We're going to do several of the parts of the Ferris wheel question all at once because they're all related, but they require slightly different approaches. What we're going to do is we're going to find out how much force the seat has to apply to the rider at various positions along the route of the Ferris wheel. And we know the acceleration, the centripetal acceleration of the rider to go in a circle. And we have a rider that's going to be on the car, the mass of which is 48 kilograms in my problem. So the different locations I'll label as this is part 2 of the question, this is part 3 of the question, and finally part 4 when he's halfway up. So part 2, when we're at the bottom, asking what's the force on the rider. Now let's think about the case of where there is no Ferris wheel, and the rider is just going to be traveling sideways at constant speed. Then the force of gravity on the rider would have to be balanced by an upwards force just to keep the rider from falling. In this case, the rider would go in a straight line. The Ferris wheel isn't going to have the rider go in a straight line. The Ferris wheel is going to have the rider curve upwards. And so that's kind of like an elevator. So there's going to be an additional force upwards. And this would be the centripetal force to make the rider go into a circle upwards. And it's only in this direction at this particular split second in time. When the rider moves a little bit, the arrow will change direction. But at this moment, we can do this, and so the force that the ride has to provide to the person on the inside is going to be the sum of these two. So the force of the ride is equal to the centripetal force plus the negative of the weight force centripetal force is equal to mass times centripetal acceleration, and we still have the force that keeps him from falling. We could do a little factoring here, I guess. Factor out the mass, centripetal acceleration minus gravity. So we have mass of 48 kilograms, centripetal acceleration of 1.6668. This is from the previous section, the previous part of the problem. Then minus a negative 9.8. So 1.6668 plus 9.8 times his mass of 48. 550. So the force that the ride has to provide is equal to 550.41 newtons up. The next part of the problem is when the elevator is at the top, and if the elevator was not the elevator, but the ride, sorry, think of it as a two-dimensional elevator. If the car at the top was just to go sideways at a constant speed, the amusement park or the ride would have to provide an upwards force this way to balance out gravity down. And then we want the rider to still go in a circle, so the rider is going to need to have a centripetal force that way. So the two forces that the car has to provide are those two. And this one's going down, so it's going to be a negative Fc. So the force of the ride is going to be equal to a negative Fc plus a negative mg. So it's a negative MAC minus mg. So if I put those in, or if I factor out the m, it'd be m times a negative AC minus g. .48 kilograms times a negative 1.6668 meters per second squared plus a 9.8 meters per second squared. So 9.8, the difference between the 9.8 and the 1.666 times 48. So it's 390.39. And in this case, it's still going to be up. Which means that the ride actually is pushing upwards on the person, even though they're moving in a circle in the downwards direction. So they're not going in a circle that they would, or in an arc that they would travel in if it was just gravity. It's a slower speed, a bigger arc, not as tight an arc as if they were just in free fall. So the last step of this is when we're at the side. The last part of the Ferris wheel, part 4, is when the car is on the side of the Ferris wheel. So it's something like this. The person inside is going to have a downwards force due to gravity. If the person was going to move in a straight line at constant speed, they would have to have an upwards force, or even just to stay stationary, they'd have to have an upwards force of the opposite of their weight. And then that would just keep them moving in a straight line. So to turn inwards, they'd have to have a center-seeking force of Fc. So we're going to calculate the net force due to the car, which is these two. This downwards one is just due to the Earth. And because they're not in the same direction, they're at right angles to each other, we're going to have to add them like vectors, where they're going to find the hypotenuse of this force triangle when I add these together. So adding them together, I would have a negative mg plus a centripetal force, and so the net force due to the car, or the ride, is the hypotenuse. So that would be equal to the square root of the gravity force squared, which is negative mg squared, plus the centripetal force, which is MAC squared. The mass of the rider is 48. So negative of a negative would be positive. So that'll be 48 kilograms times 9.8 squared plus the 48 kilograms times our centripetal acceleration we found in part 1, 1.66 squared. And I got a value of 477.154. That's a force, so it's in newtons.